Welcome to this tutorial. In this class we are going to look at special theoretical probability distribution, which are classified into two. We have discrete probability distribution and continuous probability distribution. So let's begin by looking at discrete probability distribution. Here we are going to look at the first one, which is Bernoulli distribution. Bernoulli distribution is a kind of distribution whereby we are going to have an experiment in which in that experiment we have only two possible outcomes, either a success or a failure, and this experiment is just done once. So to begin with, we are going to begin by defining Bernoulli trial, and a Bernoulli trial is a random experiment with only two mutually exclusive outcomes, that is either a success, which can also be said is the occurrence of an event, or a failure, which is non-occurrence of an event. For instance, if I have a bulb, or I'm manufacturing bulbs, so I want to check whether the bulb which I've produced is either defective or non-defective, then that kind of trial or that kind of experiment which I'll be doing will be Bernoulli, because here you can see either the bulb will be defective or it will be non-defective. So that's a very good example. Another example is if I toss a coin, I can either get a head or a tail. So here head might be the success according to what I'm defining, and then the tail can be a failure. So that is also a Bernoulli trial. So in this kind of experiment, when the outcome which I'm looking for occurs, then I'm saying there is a success. Here we give the random variable a value of 1, and if it does not occur, then we give it a value of 0. So here we are saying that let x be a random variable such that x takes the value of 1 if the outcome is success, and takes a value of 0 if the outcome is a failure. Here we are talking about failure. So we want to come up with a distribution here, and we are saying the symbol distribution is completely defined and is characterized by a single parameter, which is p. P is the probability of success, and the opposite of that one, which be the probability of failure, which is given by 1 minus p, which we use the symbol q to represent it. So in short, a Bernoulli distribution then will be given by the formula p raised to x times 1 minus p raised to 1 minus x, where x can either take the value 0 or 1, 0 elsewhere. So it means that the probability of success, then it means that we substitute the value of x with 1. So if you put x here to be 1, you'll get p times 1 minus p raised to 1 minus 1. 1 minus 1 is 0. So you can see this will reduce to p, which is the probability of success. If it is failure, then we substitute the value of x with 0. So if you put x here to be 0 and x here to be 0, this will be p raised to 0, which is 1. 1 times 1 minus p raised to 1 minus 0, which is 1. So here we are going to remain with 1 minus p, which is just but equal to q. So this is the Bernoulli distribution. Then now let's look at the moments of a Bernoulli distribution, and we are going to look at a general form. So we look for the rth moment, and the rth row moment is given by expectation of x raised to r. And since here we are dealing with a discrete distribution, then it will be the sum of x raised to r times the corresponding probabilities. And remember, the x's ranges from 0 all the way to 1. So we begin with by substituting x with 0. When we put x to be 0, then we are going to have 0 into, remember our p of x is equals to x is p raised to x times 1 minus p raised to 1 minus x, where x takes value 0 or 1. So when x is 0, you can see when x is 0, we are going to have p raised to 0 into 1 minus p raised to 1 minus 0, which is 0. And this one, you can see it reduces to what? 1 minus p. And therefore, we'll have 0 raised to r, which is 0, times 1 minus p. Next, we are going to substitute x with 1. So where there is x, we put 1. So we are going to have 1 raised to r times, so remember x is 1, so p raised to 1 into 1 minus p raised to 1 minus 1. 1 minus 1 is 0. So 1 minus p raised to 0 is 1. And therefore here we are going to remain with p. So this will be 0 times into 1 minus p plus 1 times p. And therefore the first term here will become 0. The second term here will be equal to p. And therefore the rth row moment is equals to p. So it means that any row moment in the Bernoulli distribution will be equal to p. And to be specific, the first row moment, which is expectation of x, then will be p. So it means that the expectation when we are dealing with a Bernoulli distribution is p, that is probability of success. Let's see how we can find the variance. From the definition of variance, it is given by expectation of x squared minus the square of expectation of x. Already we know expectation of x to be p, so this would be p squared. So what we need to do is to look for the second row moment. But from the calculation here, we have seen that any moment in the Bernoulli distribution will be equal to p. So it means that the second row moment will also be equal to p. So where the second row moment, we are going to substitute with p. So we are going to have p minus p squared. And you can see p is common, so we can factor it outside, and you're going to have p into 1 minus p. But what is 1 minus p? It's same as q. And therefore the variance of x is same as p times q. So next, let's see how we can find the MGF, because in our previous lesson we saw how to find the MGF, and we know that MGF is given by expectation of exponential of tx, and since we are dealing with a discrete random variable, then it will be the sum of exponential of tx times the corresponding probability. So we substitute p of x with our PMF, and our PMF, as you can see here, is same as p raised to x times 1 minus p raised to 1 minus x, where x's is from 0 to 1. So we are going to substitute accordingly, and we are going to have the sum from x is equals to 0 to 1 of exponential of tx times p raised to x times 1 minus p raised to 1 minus x. So we begin by substituting the value of x with 0. So where this x, we put 0. So we are going to substitute 0 here. We remain with exponential of 0. Here we have p raised to 0. Here we have 1 minus p raised to 1 minus 0. So exponential of 0 is 1. P of 0 is 1. So here we are going to remain with 1 minus p. Then we substitute x with 1. Where there is x, we put 1. So here we are going to have exponential of t times p raised to 1, which is p, times 1 minus p raised to 1 minus 1, which is 0. So here we are going to remain with exponential of t times p. But if you look at the first term here, it is just but q, because we said q is same as 1 minus p, and therefore the MGF will be given by p times exponential of t plus q. So we are supposed to use this MGF to find any moment, and we know we do so by differentiating the MGF depending on the raw moment you are looking for. For instance, if you are looking for the mean, we are going to differentiate the MGF once with respect to t, and then set t to be equal to 0. So for instance, for this case, if you differentiate the MGF once with respect to t, then we are going to have p times exponential of t. Then setting t to be equal to 0, then we are going to have p times exponential of 0, which is 1. So this will be p times 1, which is p, and therefore the first raw moment will be just p, as we had seen earlier, and this is same as expectation of x. With that, we are done with Bernoulli distribution. So we want now to extend this one to binomial probability distribution. Binomial probability distribution is just the extension of Bernoulli. In this case, for each trial, we are going to have two possibilities, either a success or a failure. And therefore, we are going to do those trials n times. We are going to do those trials n times. And what we form is now Bernoulli probability distribution. So this is an extension of a Bernoulli distribution. In this case, we have more than one trial, and it consists of n identical and independent trials. There are only two possible outcomes for each trial, either a success or a failure. And the probability of an outcome is the same from one trial to another trial. The random variable is the number of favorable outcomes. So remember, here we'll be carrying out the trials n times. So we are defining our random variable to the number of favorable outcomes. So the number of favorable outcomes ranges from 0, 1, all the way to n, because we are doing the experiment n times. With that, let's now define the distribution. Let a trial result into a success with a constant probability p, and into a failure with a probability 1 minus p, which is q. Then the probability of x successes in n independent trials will be given by the formula probability that x is equals to x is same as n choose x times p raised to x times q raised to n minus x, where x is 0, 1, 2, all the way to n. Remember, q we said is same as 1 minus p. Q is 1 minus p. So n choose x is also n combination x, and this can be written as binomial distribution with parameter np. So a random variable x has a binomial distribution with parameter n times p. Let's consider an example. It is expected that 10% of production from a continuous process will be defective. Find the probability that in a sample of 10 units chosen at random, exactly 2 will be defective and at least 2 will be defective. So here we are going to begin by, first of all, finding the probability that a sample of 10 units chosen at random is exactly 2 will be defective. So we need, first of all, to write down the probability distribution. So since here we have two possibilities, either having a defective or a non-defective, and therefore we can apply binomial distribution, and therefore we are going to have the probability that x is equals to x to be n choose x times p raised to x times q raised to n minus x, where x is from 0, 1, all the way to n. So what is our n in this case? Our n is 10, because we have said that we have 10 units chosen. So our n is 10. N is 10. So P is the probability of success. We are talking about defective, and you're saying 10% of production will be defective. So the probability of success is 10 over 100, which is 0.01, and it 0.1, because we are talking about 10%. Then Q, which you know is 1 minus P, it will be 1 minus 0.1, which is 0.9. And therefore, here where there is N, we are going to substitute with 10. Where there is P, we substitute with 0.1. Where there is Q, we substitute with 0.9. So we begin the first part. The probability that exactly 2 will be defective. So probability that x is equals to 2 will be the same as where there is x, we are going to put 2. So it will be 10 choose 2 times 0.1 raised to x, which is 2, times 0.9 raised to 10 minus 2, which is 8, because our n here is 10. So it's 10 minus 2, which is giving you 8. So using your calculator, you are going to look for 10 combination 2 times this, and you're going to get 0.1937. Then the next part is we look for the probability that at least 2 will be defective. At least 2 will be defective. It means that we are looking for the probability that x is 2 or more. That is probability that x is equals to 2 plus probability that x is equals to 3 plus all the way to probability that x is equals to 10. And this can also be written as 1 minus probability that x is less than 2. 2 here is not inclusive. And probability that x is less than 2 means that probability that x is equals to 0 and probability that x is equals to 1. So we are going to look for these two. So probability that x is equals to 0, where there is x, we are going to put 0. So we are going to have our n being 10, x now is 0, times p raised to 0, times q raised to 10 minus 0. So for the first part, this is what you are going to have. Then for the second one, we are going to substitute x with 1. So we are going to have 10, choose 1, times 0.1 raised to 1, times 0.9 raised to 10 minus 1, which is 9. Then if you simplify this one here, you are going to get 0.3486 plus 0.387. So this will be 0.264. So that is the second part of that problem. So below here there is an exercise which I want you to look at it. So in our next lecture we shall look at the MGF of binomial distribution.